So next I want to address the issue of path independence that we brought up before when we were integrating z squared over these various regions. So what I want to do is I want to talk about kind of an analog of the fundamental theorem of calculus. So I'm going to call this a fundamental theorem of calculus for line integrals. That's the way I think of it anyways. And what this theorem says is that for certain functions, the path is not going to matter. And so it tells you what are these certain functions. So let's assume that capital F is an antiderivative. So assume that it's an antiderivative of little f, where little f is continuous. So little f is continuous on a region. Remember, region means open and connected. Open connected set G. Okay. I don't actually have to say, just to pause for a second, I don't actually have to say that the function's continuous on the region G, because if capital F is an antiderivative of little f, then capital F is holomorphic on G and therefore differentiable on G, and differentiable implies continuous. So the continuity here is just for emphasis, but we don't really need it. So, I mean, it's implied. It's already there. I don't need to explicitly say it. So anyways, so let's let capital F be an antiderivative of little f, and suppose gamma, so let's suppose gamma is a piecewise smooth, so is a piecewise smooth curve with parameterization, so with parameterization gamma, where say t goes between two values a and b, so less than or equal to sign. All right, so we have a little function f that's holomorphic on a region G. We have capital F, which is an antiderivative. We have a parameterization gamma, which is parameterized by some function gamma of t. And so if we have all of these nice things, then it turns out that the line integral of f over gamma is going to turn out to be, I mean, by definition, we know that this is the integral of f of gamma of t times gamma prime of t dt. And then if you think about the Calc 1 fundamental theorem of calculus, this just tells you that this is just f of capital F of gamma of b minus capital F of gamma of a, right? And so the proof, I'm not really even going to say anything because you've already seen the proof in a Calc 1 course, right? If you are willing to accept how substitution works, this is basically just substitution plus the definition of an antiderivative, right? So if you were to substitute gamma of t as say u, then what you would have to do is you'd have to change the bounds as well. So you get f of gamma of b minus f of gamma of a. And so this again is just the fundamental theorem of calculus part 2 that you get taught in Calc 1 in Math 1800. And so what this tells you is that if you have a piecewise smooth curve, and if little f is holomorphic with an antiderivative, then you have path independence, right? The integral of f over some path gamma actually only depends on the endpoint. It's not going to depend on the actual path that you take. And so if we think back to the example that we did an example of the integral of z squared over different paths. And as long as so this was different paths from 0, 0 to 1, 1. And as long as those paths were piecewise smooth, then everything's fine and you should get the same answer, and we did. So that's why that works out. I'll mention that example one more time in the next video as an example. But one important corollary before we leave. So one important corollary here, and this is going to be huge, and this is going to come up again and again and again. Let's let gamma be a piecewise smooth, so piecewise smooth, closed path. So closed means that the curve is going to start and stop at the same point. So gamma is going to be a piecewise smooth closed curve or closed path on a region G. And let little f, so again, continuous, but let a little function, little f, have an antiderivative. So it's going to have an antiderivative on G. And if that's the case, then it turns out that the line integral, the integral of f over this path gamma is going to be, think about what this is going to be. It's going to be the antiderivative of f of gamma of b minus f of gamma of a. But notice that since it's closed, gamma of b and gamma of a are actually the same. And so this is just going to be 0. So this tells you that if you have a piecewise smooth curve on an open and connected set G, and if little f has an antiderivative on that region G, then this line integral, this integral of f over the path gamma is going to integrate to 0. Okay, and so this is going to be a really powerful theorem for us. We're going to visit themes on this over and over and over, basically for the rest of the semester. Okay, so we'll talk about all sorts of integral formulas that we're going to have, but this is, I think, maybe the most, this is kind of like the ground floor where we're going to get in on the, when we're talking about integrals here. So this is an immediate corollary of what we were talking about before, but a very important one.